Hello everyone, I am Subhasantanam, CSE23444. In the second half of this case study, I focused on questions that go beyond just vehicle growth and health impacts, and instead I examined how different fuel types, vehicle classes, policies, monitoring systems, and regional factors interact with air quality. These questions are designed to uncover patterns at both the state and national levels, helping us understand not only whether vehicles matter but also which vehicles, in what context, and what conditions they influence air pollution. By looking at fuel cells, vehicle categories, the impact of the 2024 SPME policy, the role of monitoring stations, and urban-rural differences. This section highlights the complex and sometimes counterintuitive nature of air quality trends in India. Other than the datasets used earlier, I haven't used any new datasets. I only incorporated a shape file for the geoplots, and the existing datasets were sufficient to answer all these questions. Now let's look into the sixth question. Do states with higher proportions of diesel or petrol vehicles show worse AQI compared to states with more CNG or electric vehicles? To explore this question, I first plotted a chloropath map of India. I noticed that states like Bihar, Uttar Pradesh, and Delhi, which have higher shares of diesel and petrol vehicles, showed AQI above 150. In contrast, many southern and northeastern states with cleaner fuels had much lower AQI around 40 to 80. Then I plotted a wiring graph to compare the distributions. Here, high polluting states showed much wider spreads and extreme values, while low polluting states were tightly clustered between 70 and 80. Next, I went deeper with the regression plot, and this gave me a surprising result, a negative correlation of minus 0.48. This meant that a higher polluting fuel cell did not always translating to higher AQI. To investigate further, I divided states into quartiles and drew box plots. Interestingly, states in the highest quartile of polluting vehicles have actually had a lower median AQI than the middle groups, suggesting that factors like industry, weather, and population density often outweigh vehicle effects. I chose maps, variant plots, regression, and box plots because together they show not just overall patterns but also exceptions, something simpler charts couldn't capture. So, in conclusion, while states with more diesel and petrol vehicles often experience poor AQI, the relationship isn't linear. Vehicle population is important, but other environmental and industrial factors also play a major role in shaping air quality. Now let's move on to the seventh question. Do certain vehicle classes such as trucks, buses or two-wheelers contribute more strongly to worsening AQI? To explore this, I first calculated the average AQI across vehicle classes. What I found was surprising. Buses, trucks, cars and two-wheelers all had almost the same average AQI values, around 102 to 104. But the electric or clean group stood out with a higher average of 110.7. This suggested that regions with more clean vehicles were still highly polluted, likely because of other dominant sources like industry or urban density. Then I went deeper using quartile based wiring plots. For trucks and buses, I noticed that states in the highest quartile actually had lower maximum AQI values than Q2 or Q3. In other words, simply having more of these vehicles didn't always mean worse air quality, probably due to better regulations, newer fleets, or regional factors. I saw a similar pattern for cars and two wheelers. The widest spreads and extreme AQI values often appeared in the middle quartiles rather than the highest. By contrast, the electric or clean group consistently showed higher AQI in Q3 and Q4, again reflecting that these are the most urban centers where pollution comes from multiple sources. Finally, I checked correlations to confirm the trends. Electric or clean had the strongest correlation with AQI at 0.31, followed by others at 0.26, and cars or light vehicles at zero point 0.2. Trucks and buses show so much weaker correlations around zero point 0.12 to 0.13. That's why I concluded that no single vehicle class is the main driver of poor air quality. Heavy vehicles do contribute, but the data clearly shows AQI depends more on the overall mix of vehicles, fuel types, urbanization, and industrial activity. I chose bar plots, wiring plots, and correlation analysis because they revealed both averages and spreads, something simple totals around could not show. Now let's move on to the eighth question. After the introduction of the SPME-PCI policy in 2024, has EQI improved and has there been an increase in electric vehicle registrations? To answer this, I first plotted the national averages before and after the SPME-PCI policy. For electric vehicles, the change was very clear. Average monthly registrations rose from about 1515 to 1772. That showed me a definite push in EV adoption after the policy. Then I explored the AQI side. I found a modest improvement. The national average dropped from 104.9 before the policy to 101.5 after. The shift wasn't dramatic, but because the trend was consistently downward, it suggested the policy was indeed helping. Next, I went deeper using state level maps. For EVs, I saw big jumps in states like Uttar Pradesh, Assam, and West Bengal, while Kerala, Tamil Nadu, and Telangana showed steady increases too. For AQI, I noticed states such as Delhi, Bihar, and West Bengal turning slightly lighter post policy, pointing to moderate improvements. Not every state improved, but overall the direction was positive. I chose bar plots for the simple before and after national comparison and choropath maps to capture the spread across states. They work better than cluttered line charts or unnecessary 3D visuals. So to conclude, after SPME-PCI, EV registrations have clearly gone up and AQI has shown a slight but consistent improvement. The gains may not be huge, but the data tells me the policy is nudging things in the right direction. Now let's move on to the ninth. Those states with more air quality monitoring stations report more stable or consistent AQI trends compared to those with fewer stations. To address this, I first plotted a scatter of monitoring stations versus AQI variability. For states with fewer stations, the points were tightly clustered, so I replotted using a log scale. This spread out the data, but the trend line was still fat, showing no strong linear relationship. Next, I compared low, medium, and high station groups with the box plot. The medium group actually had the highest median variability, and all three overlapped, meaning most stations don't necessarily give more stable AQI. Choropath maps confirmed this. Delhi with many stations still had high variability, while Himachal Pradesh with very few stations showed stable readings. Line plots told the same story. Delhi's AQI was erratic with sharp spikes, while Himachal's trend was smooth and steady, and Tripura sat in between. I chose scatter, box, maps, and line plots because together they showed both the statistics and the visual patterns, insights a simple bar chart would have missed. In conclusion, states with more monitoring stations do not report more stable AQI. Stability depends more on local pollution sources and environmental conditions than on station count. Now let's move on to the 10th question. Do urban areas consistently record worse AQI than semi-urban or rural areas within the same state? I started by plotting a violin chart of AQI for urban versus rural areas. It showed me that rural regions had not only higher medians but also a much wider spread with extreme outliers pointing to the bigger air quality issues overall. Then I went deeper with the line plot of national trends over time. Both urban and rural AQI follow the same seasonal cycle, peaking in winter and dipping during monsoon, but the rural line consistently stayed higher. To check if they held at the state level, I plotted a scatter of rural versus urban contributions. Most states lay below the diagonal, meaning rural AQI was higher, but a few like Delhi were exceptions. Finally, I mapped the differences on a choropath map, which made the contrast clear. States like Himachal Pradesh and Bihar had much higher rural AQI, while Delhi stood out with higher urban AQI. I chose violin plots to capture distributions, line plots for time patterns, scatter plots for state comparisons, and maps for spatial clarity. Simpler charts would have missed these insights. So in the end, I found that urban areas don't always have worse AQI. Nationally, rural regions tend to be worse, but state-level analysis revealed a far more nuanced picture. So, from this case study, I found that air quality isn't driven solely by vehicle numbers. Industry, geography, and population also play key roles. Policies like SPME-PCI are helping, but rural areas often have worse AQI and more monitoring stations don't ensure stability. Lasting improvement requires targeted, data driven, and region specific action. Thank you.